Imagine a world where the possibilities are endless, where everyone can participate and everyone can prosper. A world where how we live, how we learn, how we work, and how we play are all transforming. This is the world we live in now. There are already 30 billion connected devices and 200 million plus connected devices each new day. It's a world where every part of our lives is advancing faster than ever before. With 1 trillion connections by 2030, half of the world's population is on the web, where cities are becoming the centers of learning, culture, careers, and rising economies that enhance our lives. At the speed of digital, innovation is transforming our planet. From smart factories to space exploration, from virtual medicine to energy alternatives and sustainable farming, from cutting-edge medical science to the world's most advanced semiconductors, we are redefining technology to make our world a better place. Led by networked intelligence, social media, mobility, AI, IoT, and big data, we have entered the 4th industrial revolution, and it is disrupting every industry, every country, and every life for the better. At Semi, we serve this incredible ecosystem that helps make the digital world possible. That's why our new story is so much bigger, because Semi is more. Today, we're extending our reach from semiconductor design to equipment, materials, devices, and applications. We're driving value in workforce development, expos, standards, and R&D funded programs. We're providing insights and exploring new opportunities with thought leadership. We're inspiring innovation and industry engagement through our technology communities and partnerships. We hold the big conversations that drive growth, influence public policy, and help make technologies safer. And together, we fuel endless possibility. Semi. Together, we are reshaping tomorrow.
Hello and welcome to Made in 4 from Wafer to Chip webinar, Next Generation Inspection and Metrology Solution for the Semiconductor Industry. My name is Ilan Englard. I'm the European Cooperative Project Manager and Made in 4 Coordinator for Applied Material Israel. For the semiconductor industry, time is money, with demand for smaller, more sophisticated chips rising with each new generation of technology. Many manufacturers look for time-efficient solutions to ramp up high-volume production while avoiding defects when decreasing dimension and new materials are introduced. Measuring near-atomic scale modern-day semiconductor manufacturing requires an inspection to be highly precise and accurate, setting new standards on reliability and efficiency of metrology tools and processes along the assembly line. And while finding defects and fighting disruption is becoming more challenging and costly every year, it is easier and more affordable than you think to implement change and gain an immediate return on investment. Join our expert from the Made in 4 project and discover how the next generation of innovation in metrology and inspections for the semiconductor and automotive industries can help your business to drive technological improvement and increase profitability. Let me introduce you to our panel. Dr. Doni Meshulach is the Director of Technology and Strategic Collaboration in Applied Material Israel. He will present the wafer inspection and metrology challenges and innovation for advanced semiconductor technology nodes. Dr. Frank de Jong is Director of Strategic Partnership in Thermo Fisher Scientific. He will present the metrology and characterization innovations meeting the new Industry 4.0 challenges in the semiconductor industry. Dr. Juan Andres Torres is a distinguished engineer in Siemens CDA. He will present practical machine learning application for semiconductor manufacturing. And Dr. Daniele Pagano is a project manager for maintenance programs, finance project, and fab cybersecurity at STM Microelectronics. He will present the Industry 4.0 productivity improvement in major European fabs. And Dr. Yoav Hirsch, who is an R&D project manager in Tower Semiconductor, will present contact image sensors' latest innovations addressing the challenges of Industry 4.0. Let me introduce you first to Dr. Doni Meshulach from Applied Material Israel.
Hello, and welcome to Main.Info webinar. My name is Doni Meshulach from Applied Materials Israel. I'm a Director of Technology and Strategic Collaborations, and I'm happy to be here today to talk about wafer inspection and metrology challenges and innovations for advanced semiconductor technology nodes. I will start my presentation with a short background about metrology and inspection challenges, and then I will move to give some details about Applied Materials Israel main task in Main.Info, and finally I will summarize my talk. Here we can see some of the main drivers and the demand for semiconductors over the recent decades. So in the late 80s there was a huge demand for mainframe computing with hundreds of thousands of units, and then it was the PC and internet that was driving hundreds of millions of units, and then it was the mobile and social media era with billions of units sold, and more or less at the 2020s more data was generated by machines than humans. And now we're at the beginning of a new era with AI and big data with trillions of units projected to be sold in the coming years, all driven by virtual reality, augmented reality, Internet of Things, smart devices, big data, artificial intelligence, machine learning, Industry 4, and other drivers. The electronic devices we consume are basically composed of chips, and these chips are manufactured over several weeks to several months, depending on the complexity, with a few hundreds to over 1,000 process steps. And all these steps, during all these steps, it is critical to ensure that the process is within what we call the process window, so that the yield is high enough to ensure a functional and production-worthy electronic device. And this is critical that everything maintains in place, because 1 week of downtime, for example, at a 3 nanometer logic fab will result in a few tens of millions costs. So it is critical to maintain the process within the process window. At Applied Materials Israel, we develop process diagnostics and control solutions. We consider ourselves as the fab eyes. We work in the forefront of technology to provide the wafer fab industry with patterning control and defect control cutting-edge solutions. Metrology and inspection enables chip manufacturers to see clearly into the process and accelerate time to market of their most advanced technologies. On the bottom left, we can see a defect. Defect control is about finding these defects to make sure that no killer defects exist on the wafer. On the right-hand side, we see various types of structures that need to be measured, and patterning control is about measuring these structures to ensure that minimal deviations of the structures actually exist on the wafer. So metrology and inspection is about detection and classification of defects, its measurement of structures, and characterization of the dimensions and other physical properties of the structures. There are many metrology and inspection challenges. Here are just a few of them. On the left, you can see the key challenge of design rule shrink. There are denser features that need to be imaged, and the smaller defects become killer defects. Next is the transistors that several years ago have become three-dimensional. And these complex geometries have trenches, have sidewalls, and all need to be characterized. New materials were introduced, and there's no line of sight. In the center, we see high aspect ratio challenges, mostly due to 3D NAND memories, or VNANDs. And here the metrology challenges is due to the high aspect ratio geometry, and we also need to find buried defects at these extremely high aspect ratio structures. Because of the design rule shrink, process becomes marginal, and we need to look for systematic defects, and we need to ensure sufficient metrology coverage to allow some systematic and meaningful analysis. And finally, the EUV lithography, which introduces new mask technologies and new mask challenges, as well as high sensitivity requirements due to the design room shrinks. So just a few words about the process control. So here we can see a process window of any parameter. In this case, we chose circuit performance example, and we can see two distributions. And here we look at the speed of the transistor. So we can see some kind of a variation of the speed of the transistor, and circuit performance is gated by the slowest transistor. And lower transistor variability means higher device performance. So really the objective of the process control here is to get the mean to target and control this parameter to a very tight window. And here, for example, these distributions may indicate on various performance across the wafer, with the red dots indicating a bad die, which is out of the control limits, and the green dies indicating a good dies within the control limits, but still there's a distribution of these parameters. So process steps introduce variations across the wafer, and in this example it's truly across the wafer, but we can also look at other spaces of variations which we need to control within. So here we see the two extremes. On the left, we see no sampling of a wafer. We have no idea what is happening. On the right-hand side, we see massive metrology and inspection information. So just imagine you have only few sampling points, so you can barely see the picture or understand what's happening on the wafer. But if you improve your productivity or your sampling and increase that to a level of massive sampling, begin to view your image. Finally, you can see the big picture. So massive sampling reveals hidden information. So obviously, you need to increase your sampling to extract that information. And here's a beautiful example. Here's a sparse sampling of some kind of parameter across the wafer. And here we see more massive sampling, which reveals some kind of a signature. And the more sampling that we apply, you can see eventually a true signature, which helps to identify a process issue, and this shortens time to root cause from days to minutes. So it's really important to have a massive sampling to reveal process-induced issues. This graph shows the value of time to market. The x-axis corresponds to time, and the y-axis corresponds to yield or profit. And the whole idea is that you would like to reach high yields at shortest time. And any deviation between your target and your actual performance is really translated into billions. So the whole idea of metrology and inspection is to drive your process as fast as you can from R&D through a transition of ramp and acceleration to high volume manufacturing. Let us move now to Applied Materials Israel main task in Maiden 4. We had multiple tasks in Maiden 4, but two of them were significant. The one was about optics wafer inspection, and the task was to improve optics wafer inspection sensitivity to keep up with the shrinking size of killer defects and provide new information, while improving throughput and productivity, and we did this through new optics, high performance computing, and overall system design. The second main task was about e-beam wafer inspection, and the idea was to improve e-beam wafer inspection sensitivity to keep up with the shrinking size of killer defects and provide new information and expand application space, while improving throughput for massive across-wafer scanning through development of a new column, modules, and system design. So overall, we improved the sensitivity, the productivity, and provided new information related to defectivity and metrology. Our developments in Mating 4 were made possible through multiple collaborations. So we collaborated with Leti and IMEC. They provided us with advanced wafers, which were used to validate our developments. We collaborated with Nanomotion on stage and positioning. We collaborated with Mentor Graphics. We provided them raw data for their developments of new metrology through across tools machine learning analysis. We collaborated with ICT that developed the E-beam inspection column. We collaborated with OCO Technologies in the development of bright field optical inspection concept, and we collaborated with ProDrive on bright field image processing and data handling for the image processor of the tool. Let us start with the optical wafer inspection. A module that we've been exploring is the use of an adaptive wafer control for high sensitivity and matching. And the idea is shown in the top left, where an adaptive scheme is used to compensate for any residual aberrations that may occur in your optics system. So if you correct for your aberrations, your optics performance improves, and therefore your sensitivity improves and your matching. On the top center and the top right, you can see some prototypes which were developed by OCO. On the bottom left, you can see some very nice wavefront generated by the deformable mirror, which was developed by OCO. On the bottom right, you can see some on-tool images showing some test structure, and you can see as you move from left to right that the contrast is improving as your wavefront error is reduced. So basically, OCO was able to develop a module, adaptive wavefront control, and we were able to find a calibration method to control all the various actuators and phases of that mirror in order to generate any waveform to compensate for aberrations and thereby improve the sensitivity on tool. Yet another development is what we call automatic laser beam parameters control. And the idea here is to develop a module which will improve our sensitivity, repeatability, stability, productivity, and matching. And the motivation is that if you have a laser light source on your tool, that laser deviates a long time and changes a long time. So after some time, the performance of the tool degrades and you need to perform a maintenance in order to recalibrate the tool. So the idea was to develop some kind of an automated feedback to keep the spot size in both X direction and Y direction, as well as pointing stability and other parameters within a very tight window. So we developed that module you can see on the top right. And in the bottom, you can see some results for the spot size measurements. There are other parameters that are also controlled. And you can see that the spot size, both in X and Y, are controlled within a very tight window using this module tool. Yet another important feature is the improved sensitivity. So you can see here defect counts for two types of defects, type 1 and type 2. And you can see here 3 points of measurement. The left measurement is an ideal tool or well-calibrated tool. The midpoint is a tool after we let the tool degrade a long time, and then we commanded the module to recalibrate the tool automatically, and then the tool was recalibrated, and again the defect count was increased. So if this is done automatically during production, we maintain the high sensitivity, stability, and of course matching. Yet another development is what we call flexible optics mode, and the idea here is to develop a new optical mode to find more types of defects and show higher sensitivity and productivity. So we use the IMEC 4-chip devices on a Mont Blanc wafer, and on the top we can see some defect counts of various types of defects. The green indicates the new modes, and you can see that the green is performing better on type 4 and number 5. And on the bottom, we can see that not only we were doing better in terms of detection, we also managed to improve the throughput of the detection on on these defects. So overall, we have a higher sensitivity and higher productivity. Coupled to the developments of the optics, we also developed a high-performance computing system, and the main challenges here were to to manage high data rate acquisition channel with incoming data rate of tens of gigabits per second, execution of parallel computer vision algorithms and advanced deep learning algorithms, massive real-time processing power to support complex algorithms, and massive data communication with advanced periphery systems and huge storage volumes. And this architecture needs to be scalable to support future algorithms and computing technology, namely hardware and software. We also need to address environmental requirements such as low power consumption and heat dissipation limitations, high reliability requirements, fab node restrictions and limitations, computing system cabinets and footprint limitations, and everything must have a high cost performance in order to meet some cost targets. And this development was conducted together with ProDrive. So the methodology we took in this development was the use of off-the-shelf components, hardware and software, including open source to accelerate development time. But the use of off-the-shelf components implies that the focus moves to a system which required optimization of hardware and software architectures, processing dispatching, load balancing, and the solutions included the use of tailored server architecture for the specific use case, use of accelerator and GPU for specific use case, and design of data acquisition platform detectors with off-the-shelf components. And here we can see a snapshot. On the right, we can see the computing cabinet module, which is a complex module of its own developed by ProDrive. Bottom left is the high data rate grab module, which was developed by ProDrive. The top left, which is a scheme of the computing system, which is scalable for the bright field inspection. And in the bottom right, we can see end-to-end defect detection on programmed wafer defects metrics, showing that this high-performance computing system was integrated successfully and is yielding the required detection. We also demonstrated our detection on a Leti DSA wafer. So here we received a directed self-assembly wafer, and the objective was to detect DSA process-related defects with focus on small defects. So the bottom left shows a nice Pareto of multiple types of defects with focus of bridge and dislocations. And on the right-hand side, we can see some of the beautiful small defects we found of dislocations and the champion defect of the order of 10 nanometers, which is quite significant, with very good feedback which we received from Leti versus the baseline that they use. In addition to this work, we also provided significant massive raw data to Mentor Graphics for their development of machine learning algorithms to provide new metrology information for analysis of data acquired by various inspection and metrology tools. So we received 10 wafers from IMEC, and we scanned each of these wafers by multiple modes and provided the raw data to Mentor Graphics and for their analysis of using the various signatures that we found for their analysis, which combines various metrology tools for improved metrology, and this will be reported elsewhere. The second main task we had in Mating 4 was about e-beam wafer inspection, and the motivation here was higher sensitivity and productivity. So in order to improve the throughput or productivity, we increased the current density of the source. And in order to improve the imaging performance, we developed new detector, and we improved the landing energy of the electrons to provide more information about the wafer that we're scanning. The new key modules include new column developed by ICT with new detector, new electron emitter and improved detectors. System development includes electronics and controls, motion algorithms, and new acoustic enclosure. And the higher throughput was enabled by the new color and by the improved detection. And the improved application space was enabled by improved detection and the higher length imaging. A new detector was developed for improved performance, which enabled new imaging that can be extracted from the target, which expands the application space, and higher throughput at new working points. And such an example you can see at the bottom left showing the baseline imaging, and on the next to it, to the right to it, you can see improved imaging showing particle transparency due to improved detection. So basically, new information is available to the application user. To validate the performance of the new tool that was developed, we again used the IMEC forksheet devices, and the results are shown here. On the top left, you can see a baseline defect, and in the center, we can see the same defect at the same resolution, but a significantly higher throughput. And on the right-hand side, we can see a better or higher resolution image of that defect at same throughput. So basically, we have higher sensitivity. They're also shown bottom center at the bottom small void defects and small residues, bridging defects, all indicating about the very nice sensitivity of the new tool on these advanced devices. Just like we did with the Brightfield tool, we also provided across tools, across wafers measurements. We performed and performed inspection and provided the raw data on 2 of IMEX wafers, and we provided these results to Mental Gothic in their work to provide new metrology information through analysis of data acquired by various inspection and metrology tools from same wafers. So to summarize, Applied Materials Israel developed as part of Mating 4 optical and e-beam inspection platforms to address the metrology and inspection challenges of advanced semiconductor manufacturing, which are high sensitivity, high productivity, and new metrology information. The sensitivity, productivity, and new metrology information developments were made possible through multiple module level developments as well as system level designs, and the sensitivity and productivity were demonstrated with IMEC and Brightfield wafers. And all these developments were made through collaboration with multiple Mating 4 partners, just to name Leti, IMEC, Nanomotion, Mento, ICT, Aqua Technologies, and ProDrive. So thank you for your attention in this presentation. Finally, I would like to acknowledge and thank the European Commission and Excel JU for their generous support and funding of this project. And I would like to thank all Applied Materials Israel colleagues and all Mating 4 partners for collaborating in this successful project. Thank you.
Ladies and gentlemen, it is my pleasure to discuss with you this afternoon some of the developments which have been taking place in the Maiden 4 project around metrology and characterization, meeting the new challenges of Industry 4 in the semiconductor industry. My name is Frank de Jong. I am a Director of Strategic Programs in the Materials and Structural Analysis Division of Thermo Fisher Scientific. And my role in this Maiden 4 project has been to lead the work package on metrology platform developments. The agenda for this presentation looks as follows. First, I would like to address the key challenges and objectives which we have formulated in the project for metrology in this new demanding era. Then I would like to show a couple of improvements which we have achieved and show a few examples of the metrology platform developments. And finally, I would like to address the fitness, the maturity of the metrology platforms for Industry 4. The main challenge as formulated in the Maiden 4 project for the development of metrology platforms can be formulated as follows. It is to address a higher complexity of samples which we have to measure, and also at the same time achieve a higher productivity. This has led to formulating the following key objectives: to develop and qualify new metrology platforms which address high productivity for instance, metrology, but also inspection and characterization tools, but also address higher complexity of the samples. It's also referred to as booster 1. In addition, we've also formulated an objective to make sure that those new tools are maturing and more ready for what is called Industry 4 challenges. That has to do with, for instance, producing higher data rates, but also connectivity of the tools to other tools and to the fab systems. So that in the end, the factories are able to use the metrology for data analytics. This is also referred to as Booster 2. The Main 4 project is a continuation of the 3D Advanced Metrology project, which ran a couple of years ago and which was coordinated by myself. Let's look a moment into those challenges for the metrology, and those have to do with a couple of things. In the first place, denser and smaller features. There's still going on a shrinkage of the transistor and memory devices into smaller features. In addition to that, the third dimension is explored more and more, and we see complex geometries both for memory, 3D NAND, as well as gate-all-around and FinFET type structures, which are more difficult to measure. That means that, for instance, there is a more demand for high aspect ratio devices to be measured. In addition to that, there's also a continuous drive to narrow the process windows. And this means that the metrology has also to make sure to, in that respect, keep up with the shrinking dimensions and the shrinking process windows. In the Main 4 project, we have been looking at metrology platforms based on electron beam, optical, X-ray, and scanning probe microscopy techniques. And I think that the main challenge can be put as forward there is that we have a throughput challenge. At high resolution, we have to probe smaller volumes, we have smaller interaction volumes, so we have less signal. At the same time, we want to have better signal to noise in a shorter time. To achieve this, the Main 4 project has worked on better sources, better detectors, new modalities, improved sample handling, and a lot of automation and software developments. I will discuss a few examples. I would like to point out that actually the first example has been already discussed in the previous presentation around faster wafer inspection and metrology tools. The first example I want to briefly discuss is work performed by Nova on optical OCD. And what they have achieved is to develop both a standalone and an integrated new OCD tool, which has an added functionality of extra optical channels. So that means that they are able to obtain more information from a sample, and because it is integrated into the process tools, it is also faster and has a faster access. They have multiple use cases, both R&D and pilot line, as well as for complex CMD and edge layers, which they are measuring. Another example concerns scanning probe microscopies for metrology, which has been achieved by near-field instruments. And what they have done is to achieve a much higher throughput in that technology. The technology is used to measure top-down in a non-destructive way high aspect ratio devices, for instance, after etch. They have achieved this higher throughput by using a smaller scanning head and lighter, which has a way higher bandwidth. And at the same time, by integrating 4 of those scan heads into their tool. And in total, this means that their improvement in throughput is about 100 times larger than what was traditionally the case. As a final example, I would want to spend a bit more time on the work we've done in Thermo Fisher around the TEM workflow. The TEM workflow is ideal to obtain local atomic scale information. And what we've tried to develop is to do this also at high volumes. The TEM metrology workflow starts with a wafer and then uses a dual beam device to cut very tiny TEM lamella out of that wafer. And tiny, you have to think about microns. Those lamella are then transported into an electron microscope, which then yield all types of different information, both including dimensional metrology as well as compositional analysis. The first challenge to be addressed here is that those minute TEM lamella need to be transported from one tool to the other. And in the framework of the Maiden 4 project, we have developed, with the help of the SEMI organization, a standardized TEM lamella carrier, which is really indispensable for automation. So it enables a further automation of the transport of these TEM lamella from one tool to the other. A second challenge which has been addressed concerns the automation. And to appreciate that challenge, I think it's good to explain that there's many different questions being asked from the TEM tools. This could concern dimensional metrology, as I already explained, could be inspection, but also compositional analysis using energy dispersive X-ray. And each customer has different questions for each sample. So what we have to do there is to automate the acquisition of data while retaining flexibility for the customer. The work in the Maiden 4 project has led to a dedicated application software which we call Smart Automation for the TEM workflow. And this Smart Automation does not only automate the acquisition of the different types of data which are desired, but I think more impactful, also helps to automate the setup of experiments which is empowered by machine learning. After the process is started, the user is guided through a series of steps of questions and automated image acquisition to set up the experiment. And this ranges from imaging the TEM lamella as a whole at very low magnification, aligning the TEM lamella with respect to the electron beam, and then zooming into the device line of, in this case, a gate-all-around structure. Then the experiments are further defined to either acquire TEM data or, if required, acquire STEM data, which uses a scanning probe, and that then can also be used to acquire energy dispersive X-rays to generate compositional maps and profiles. If the experiments are, once the experiments are set up, a experiment card is generated in which all the data are put together to really run the experiment. And this experiment can then be run on the current sample, but also on future samples. So that then means that at that moment, the tool is ready to acquire the data, and many different types of data can now be acquired. For instance, in this case of the gate-all-around transistors, you can see that here there is a dimensional metrology performed using scanning electron microscopy techniques, but also energy dispersive X-ray is used to measure the composition of the layers which are around the silicon channels of the gate-all-around structures. And because we were able to generate many data, we are now also able to generate statistics, and in this case you can see that there has been a bimodal distribution of some of the relevant dimensions. And this is data which is really difficult to get in any other way. As a final topic for this presentation, I would like to touch upon the the use of metrology platforms in industry for environments. And the way how this can be viewed is to see them as cyber physical systems. So they are cyber because they're connected in their software to other tools and to the fab host and things like that. But they're also physical. We're not talking about web applications. The generic evolution of these cyber physical systems to fit better into the new Industry 4 ready fabs is displayed in this picture, where in the first steps a relatively simple digitalization is achieved, but then in the subsequent steps more and more intelligence is put into the systems, so that at the end of the day the aim is to have predictive capabilities and also adaptability of the tools, so that they correct themselves based on what is requested. In the framework of Made in 4, we have worked on various parts of this evolution. And in fact, in the previous slides, I already showed you about smart acquisition and smart tool setup, which relates to visibility and to transparency, so that the user knows what is going on in the tools. And in the final slide, I would like to briefly touch about on the area of adaptive tool readiness. Because the tool readiness is a very important part of the cycle of running jobs, checking the status, and if the status is not okay, measure and validate what the status is, and then perform corrections on the tool. Report on those corrections. If the corrections cannot be done automatically, then surface that and call for help. And if the report is positive, then the next job can be run. I already explained that the TEMs are very versatile tools, and that means that many different parameters need to be checked. We have identified about 18 critical tool alignments, which need to be checked on a daily or at least a weekly basis. By running them automatically, it's also we are able to also be less dependent on the operator skills which are needed. So the tool readiness checks are adaptive, and that is an important point. It means that it's not like all parameters are aligned once a week, but the alignments are called by the experiment. So if a certain experiment is being performed or wants to be performed, it automatically checks whether alignments are needed, for instance, for process navigation or device centering, or whether the image quality was still sufficient from the previous job. And if the alignments are not correct, then the alignments of those specific parts are performed until they are correct, and then the tool is ready for further use. So this is an adaptable tool readiness. So this has led to an automated STEM metrology workflow, which we sometimes refer to as fourth generation automatic STEM. I've explained that this uses smart automation, dedicated application heavily using machine learning, but it calls upon smart alignment features and tool readiness in an adaptable way. As a result, more consistent data can be formed, and there is a constant monitor of the data quality. We're able to perform metrology, dimensional metrology, with less than 1% accuracy. So this means that now higher volume TEM data can be obtained in a much faster way, which makes these type of tools also relevant and important together with other tools to work in an Industry 4 type environment. This leads me to the conclusions on the metrology platform developments. I've shown that the main challenge which has to be addressed is to enhance the productivity, but at the same time address the higher complexity of the samples under investigation. I've presented a couple of examples where significant improvements have been reached in platform development. Not only the TEM metrology workflow of Thermo Fisher, but also the inline and integrated multi-channel OCD tools of Nova and the multi-head scanning probe microscopy tools from Near-Field Instruments. Finally, I have briefly explained the maturity evolution of those metrology platforms and to look at them as cyber-physical systems and how they can be integrated more and more in an Industry 4-driven fab, which is ready for data analytics as well. This brings me to the end of my presentation. I would like to thank you for your attention. I would like to acknowledge the inputs of Nova and Near-Field Instruments, the help of the Made in 4 coordinator and the SEMI-EU organization, and various Thermo Fisher colleagues.
Hello, my name is Andres Torres and I am from Siemens CDA. Today I will be presenting practical machine learning applications for semiconductor manufacturing. This is work that has been performed on the Made in 4 project. In this outline, I want to showcase the difference between social media and semiconductor manufacturing from the point of view of machine learning. Then we will focus mostly in how machine learning models can be used across multiple applications, focusing on single process modeling, multiple process sequences, and preventive maintenance. 3 distinct applications that are needed during semiconductor manufacturing. What are the differences between machine learning applied to social media or semiconductor manufacturing? Why is this important? This is important because a lot of the techniques that have been developed have come from Google, from Amazon, and they have been focused on trying to understand human behavior. They rely on a relatively small number of measurements per user, many users per month, and this leads to data sets that are narrow and deep. That's one of the reasons that a lot of people consider this methodology deep learning, simply because there is a lot of data that needs to be analyzed, processed in order to generate successful models. The case of semiconductor manufacturing is different because while we are not trying to model human behavior, we want to model the physics involved in the manufacturing process. The number of samples are not as high as the number of samples that we will have in the case of human users, but we have physics on our side. This leads to have wide and shallow data matrices. So the techniques that are actually used for semiconductor manufacturing from the point of view of machine learning are going to be slightly different. One of the activities that sometimes is not highly discussed in social media, which is feature engineering. Feature engineering is the ability to try to extract the characteristics of the inputs of the system in order to try to use them, in order to try to relate them back into the observable output. Well, the first example is for a single process, in this case, chemical vapor deposition. We want to have a model that is able to describe how a distinct set of populations in which we have low thickness, medium thickness, and high thickness, because there are 3 distinct technology nodes that are being manufactured within the same manufacturing tool. This provides a benefit in the sense that we can actually utilize the behavior of all of these products that are being processed at for different technology nodes in the same tool and basically leverage the information across each other. We demonstrated what is the benefit of incorporating design features. In other words, the ability for the model to learn what happens in other technology nodes or from other different products in order to fully characterize the process. If we don't include any design information, the mean absolute error for that particular model will be around 16%. For example, for these high samples, it will be relatively small for the average product, and it will be slightly higher for these low examples. By creating models that are product specific, meaning that the design ID is included, that is used to distinguish between different products, we can see how the mean absolute error decreases. But more importantly, there is a methodology in which we can extract characteristics of the design, not use the design as a category, but rather as a separation on its components that further reduce the amount of error, basically halving from 4% to 2% in this extreme environment. So the more that is known about the interactions across different products, the better the equipment characterization is, And this enables virtual metrology to be performed not only in previously observed products, which will be the case of the design ID, but also for products that have not been manufactured. This is another example. We want to identify the root causes of abnormal conditions. After we have generated such models, we can identify what are the characteristics or what are the parameters that lead to low thickness conditions or high thickness conditions. Machine learning techniques like Shapley allows us to determine what are those main contributors. So while the first two contributors correspond to a previous metrology measurement and a process parameter, you will see that what makes product to have low thickness condition, it's dependent on certain design parameters, metrology parameters, and process parameters. But this order changes when we are looking at some of the higher conditions. In other words, the characteristics that lead to a low thickness or a high thickness condition, they are different. And this allows us to identify what are the root causes of the conditions that are leading to out of control thickness. We describe how feature engineering is paramount in order to successfully utilize all of the information that is present. In this case, for an electroplating tool, we need to undergo feature engineering. We need to understand what is the physical behavior of all of those different parameters, extract characteristics that are relevant to all of those different parameters, and then we can also create traces within time of those newly extracted conditions. The timescales between these two graphs is slightly different. This is a duration that it happens during the one cycle of operation for one particular wafer. These signals, then they can be combined in order to identify when there is a condition, the system is going to fail, where maintenance has been performed, and what is the new state of that particular system. In the simplest of cases, one variable can actually explain the observed behavior, and therefore that actually can serve as the indicator that preventive maintenance needs to happen. Not all the systems are as simple. In the case of a chemical vapor deposition tool, basically we have raw input data that it's been collected. We perform feature engineering to characterize how that raw input data changes over time, and that creates a trigger model that is able to identify and forecast when the machine will actually be out of control. As the data is being collected during manufacturing, you are going to have some amount of data. There is going to be a delay in which this data is going to be then processed from the point of view of training. During prediction, there is going to be a model that is being used in order to monitor the behavior of that particular process. But when new data becomes available, that should trigger the characterization of new models. One of the biggest questions about machine learning is, how do we know that we are improving our model? We can perform an analysis of the contributors. When we create a model that is training 7 products, we see that we are only able to explain about 40% or 38% of the variability. As we add 2 additional products, we are able to explain about 57% of the variability. And when we have 11 products, we are able to explain close to 77% of variability. What is the difference between these two columns of pre-made in 4 and post-made in 4? In pre-made in 4, the state of the art is that virtual metrology relies on individual models that are interpolating within those types of measurements. So we will have, for example, one metrology step, another metrology step, another metrology step that are not fully measured. However, when we want to make a prediction on the e-test, well, what happens? What happens is that we don't necessarily have a full stack. We do not know in that particular region of the wafer what were some of the other observations that we had. With the work that we have done in Made in 4, we can actually construct a full description of how every single process step is virtually constructed. And that means that for every single point that we have at the end, in this case, the electrical measurement, we have a full stack of the different measurements that are accounted for. We can see how, from the point of view of e-test, the error decreases from 0.3 to 0.26 to 0.18, but also you can see that the confidence interval, it also gets tighter. Something that, again, illustrates this problem of very low sample conditions. We want to generate a model for these 2 individual wafers that are going to be explaining what the thickness is, and we are going to consider what happens when we add information from inspection tools. What we can already start seeing here is that while some thickness values improve and others degrade, the improvement or the degradation in the model quality under these low conditions, it's an indicator that other effects are present. So let's take a look at now a case in which most of the wafers are fully measured, and this permits leveraging learning across multiple wafers within the lot. In this particular case, they are 13 different electrical tests. So what we can actually see here is that if we are taking a look at the best performing case for this e-test 2, the error reduction applying the technique, it's about 41.8%. It gives us an idea of what are the main contributors to all of these different e-test conditions. These three different metrology steps that are consistently measured in the top 20 most important contributors. Now, what happens if we have now a large sample size? When now we have thousands of wafers, we are going to perform a very, very similar analysis in which we want to take a look at, after the full process sequence, what are all of these different targets or probes that need to be extracted that are able to identify what is the benefit in the electrical test. In a similar fashion as what we were showing in the previous example for back-end of line, this is the mean absolute error. If we use a technique that, again, it's pre-Medin 4, in which we are subject to the fact that there is data missing, we can see that there is a certain amount of error. But if we are able to fill in the blanks of basically creating all of these intermediate models, that now then the model can actually be concatenated in order to make an explanation of a final observation, we can see that there is an error reduction of about 47%. And this is significant because, again, what this is basically saying is that by having the same number of physical measurements, we can fill in the blanks, generate those intermediate models, create a model that now utilizes those virtual measurements, and we can improve our accuracy by 47%. I want to acknowledge the Excel, Medin 4, and the European Union, and also recognize the fantastic efforts made by Medin 4 partners, especially Global Foundries, Applied Materials, ST, Bruker, Nova, IMEC, and KLA. Without the collaboration of all of these partners, none of the data that it was presented in this presentation would have been possible. Thank you.
Good morning. It's a great pleasure to have the opportunity to highlight some important achievement that we got during the Medin 4 project. It's very interesting because we focus our attention on Industry 4.0 and the metrology application that we can have in semiconductor and automotive environment. To give the context in which we are working on, we will talk about Medin 4 project and some cases that we analyzed inside the work package devoted for semiconductor. For example, I have the opportunity to summarize the main results in improvement of DOE procedures and development of metrology tool for specific application, and we have a special focus for new materials and substrate. Furthermore, we discuss about advancement on process control and predictive maintenance. Finally, some observation regarding the interoperability for predictive maintenance on both domain, automotive and semiconductor, and a conclusion with an outlook and an opportunity on exploitation of these results. The Medin 4 project is involving 10 countries and 47 partners coming from manufacturing, metrology, academic, and also solution provider. From my side, I am the work package leader, work package 5, in which we implement what was developed in previous work package in terms of new equipment, new approach, and also new methodology. This work package was divided in two main tasks. The first one is devoted to semiconductor activity, and the second one on automotive. In any case, we have the opportunity to collaborate tightly with a lot of partners coming from other work packages. For example, for work package 3, for tool and metrology partners, for work package 4 regarding the development of a new algorithm and method, and is very important also the interaction inside the work package 6 regarding synergy and standardization. For our work package, the main objective is focused on IoT methods and new metrology tool. Is a task very important to increase the productivity, but first of all to speed up the development of new product and new technologies. In particular, regarding the work package 5.1 for semiconductor environment, I have the opportunity to describe some use case and the main results that we achieved. In terms of improvement for design of experiment procedures, is very important taking account that when we talk about new technology, new substrate like silicon carbide, it's very important to reduce the real test that we need to develop a DOE. For this reason, it is mandatory to develop and increase the efficiency in terms of virtual DOE. For this reason, we analyze 3 use cases regarding silicon trench plasma etching, for silicon nickel silicide laser formation, and thick copper electroplating deposition. For this case, it is very important to reduce the amount of tests that we have to perform, because the cost, but also the time needed to perform all the tests and evaluation. The result was impressive because we reduced by 10 times the number of tests, and also we obtain this type of results including an hardware usage in terms of CPU time needed to perform these simulations that is reasonable for our scope. When we talk for the first use case regarding silicon carbide trench plasma etching process, we got a great results in terms of the correspondence between simulation and real case, and we have the opportunity to take in account the full structure, including also the photoresist residuals that we have, because the whole structure include photoresist, the hard mask with the silicon dioxide and the silicon carbide. In this case, it's possible to reproduce at the best time the structure and the profile that we have at the end. Another case is related to the laser annealing for nickel silicon carbide for the back junction formation. It is very important because we have to guarantee the lower resistivity and also to have the right level in terms of uniformity. If you see on the left, you can see an image in which you find the two structures related to the carbon and the alloy that is a formation that we obtained at the end. Was very important because with the support with our partner, it was possible to define the process, to characterize the process window, optimize the process, and all these results are obtained reducing the time and reducing the number of tests needed to analyze the whole opportunities and variation that we can and have to take in account in this process. The last one is the thermal curing after copper electrochemical deposition. It's very important because this type of process induces a warpage, a significant warpage along the wafer. So, thanks to this simulation, we have the opportunity to define the temperature, the right temperature to perform the annealing and minimize the warpage, but also was an opportunity to understand the physics underneath. We introduce the Preisack elastoplastic approach and we understand the performance of the layer after more than one cycle. Also in this case, we reduce the amount of tests and we obtain this additional information thanks to the virtual approach developed by CNR with a CPU usage reasonable for our approach and our expectation. At the end, it was very important to increase the capacity of our standard DOE, introducing this new virtual DOE, taking account new material, new product, and a new process. In this way, we speed up the development of the process, and for sure we can use the same algorithm for next development. So it's not an activity that is limited to this use case, but we have a tool to analyze in the future other processes with that are based on this new technology. About the development of metrology tool, it was very interesting because faced the difficulties to analyze some elements present as contaminants on the surface of silicon carbide substrate like vanadium, titanium, and at the same time obtain results in a reasonable time frame. Is important because usually this type of analysis are performed only offline, are not present inside the standard production flow due to the fact that the duration of the measurement is high and impact more than a couple of hours. But the CNR, Bruker, Xilium, and PTB worked on this topic, starting from the preparation of the reference to define the tool, and the key point was the introduction of a new source, the kappa source, that allow us to detect this type of elements and at the same time speed up the time of the measurement itself. Another important topic is regarding the process control. And in this case, we analyze an equipment for copper electrochemical deposition. In this case, the structure of the tool that we analyzed is formed by 6 process chambers. So, in practice, we measure 6 wafers for each lot. Consider that when we talk about lot, I mean a box with 25 wafers. So typically, for each lot, we measure 6 wafers. But it's very important to reduce the frequency of the measurement. So the objective is no more measure every lot. But another important point is related to obtain a prediction on the remaining wafer inside the lot, because it's important to intercept just in time some drift that could be generated by oscillation in equipment parameters. This work was very important because the partner working with us developed alone different algorithms, but the activity, the interaction inside the team allow us to increase the performance of each algorithm. So at the end, we obtain the results better that we can have if we work really alone for a specific algorithm. But it's not the only gain that we obtain, because analyzing different algorithms, different approach represents a great opportunity also for us to analyze a different architecture. So to verify not only the efficiency of the algorithm, but also the efficiency of the architecture. For us it was an opportunity to understand better the performance for each approach and the benefit that we can take from each of them. For sure, the predictive maintenance is another important topic, and in general, the importance of predictive maintenance is based on remaining useful life. This is an important indicator for the parts under analysis when we have no other way to catch a drift, a problem. This is typical when we have a damaging of the parts in the sudden way, so it's not possible to stop the tool before the problem. In this case, we have no clear message from the machine and no signal from the external measurement. So we only, when the problem appears, we have the opportunity to verify what happens on the machine. So it's very important for this case put in place a predictive maintenance. We analyze two cases. One regarding the same tool that we verified before, electrochemical deposition tool, and in this case analyze the pin that hold the wafer during the process. Another case regarding the chemical side deposition process, and is the clogging of injection valve. So, you can see the tool that we're talking about and the process chamber. In this case, the pin is the part that is directly in contact with the edge of the wafer, and the risk is rapid damaging of this part. So, thanks to our partner, we analyze the image and we take under control not only the problem, the issue that can happen, but also its persistence, because we verified that sometimes some water drop, humidity, or other different particle can seems a failure on the top of the pin, but really is not. For this reason, thanks to this approach, is possible not only to catch the problem, but reduce significantly the number of false alarms. Consider that at the beginning we put in place a time-based PM, preventive maintenance, so we replaced this pin every time, also in good condition, and so bring to increasing in terms of total down and also in terms of cost, for sure. Now it's possible to take under control these parts and avoid this waste. For the other case, regarding chemical oxide deposition, we analyzed two different family tools, Centura platform and producer platform. The distribution of the gas TOEs is the same, and for both equipment could be a big problem, a clogging in this part. So at the end we have an anomalous thickness that is the results of our process. So at the end, the thickness of TOs that we grow on the wafer is not the value that we want. To avoid this, thanks to the machine learning approach, it was possible to intercept in advance the problem and also reduce the false alarms. Consider that in this phase we are testing our algorithm, and we plan to release in production in a couple of months. The last point is very interesting and is related to data interoperability for predictive maintenance. Thanks to Maven 4, we have the opportunity to analyze and test the same software, for example, used in automotive domain, to intercept a potential issue in semiconductor, and vice versa. Consider that we use this case to analyze and test the EPON software typically developed for semiconductor, and we used this approach on our epitaxial reactors, and at the same time we test this software to analyze the and predict the engine test at FCA. Vice versa, we use the AVL software developed for automotive for our reactor. And the conclusion was interesting because considering that for sure we have different database distribution, different sensor in terms of quality and number of sensor itself, but at the end it's possible to use the same algorithm, the same approach in a totally different domain. This is also another opportunity that we can exploit at the end of the project. To summarize the results, for sure an important point reached during the project is the collaboration among the partners, because working on the same topic, different partners, each of them had the opportunity to improve their own algorithm and also to verify better the performance and the opportunity that we can have. Another example of this approach is the interoperability of the software for predictive maintenance that I described before. For sure, all the activity that we put in place, for example, the introduction of the virtual DOE for new materials, or the approach development in terms of machine learning for virtual metrology and the same predictive maintenance, are usable and represent an opportunity to exploit the results outside the bound of the project. I want to thank you for the attention, and anyway I am available to give you more details after this webinar. Thanks a lot.
Hello and welcome to my session in this webinar. My name is Yoav Hirsch and I'm a project manager in Tower Semiconductors at the Sensors and Display business unit. In this session, I will cover the following 4 topics. I will recap for sure the meaning and challenges of the Industry 4.0, just to make sure we're all on the same page. Then I'll give an example of such a challenge from the semiconductor perspective. I'll talk very briefly on machine vision, use case, and finalize with advanced sensing technique. But let's start, as I've mentioned, with a brief and quick review on Industry 4 term. Let's see where Industry 4 is related to the previous revolutions. All of the 3 past revolutions are characterized with hardware and procedures. Mechanized industry is the first revolution, mass production assembly line is the second, automated production is the third, computers and PLCs govern the production with very little human interaction. In this revolution of Industry 4, we want to give the machines awareness. This is artificial intelligence and machine learning. Obviously, the complexity increases. Another term which is widely used in Industry 4 and highlights the complexity is the term cyber physical system. What it means is basically an interaction of physical items and computing at all levels, all in, sensors, actuators, sub-assembly, production parts, you name it. And in the heart of this CPS lies the core information center. So now we have many sensors to gather data. we get a tsunami of data. Data is the new oil. There's no problem to gather data. Sensors are being added constantly in both brownfield and greenfield. But what is missing in this slide? What do we do with all this data? How do we convert this tsunami of data into useful information? The missing link is how to translate vast amount of data into useful and manageable information. If we assign context to be more precise, to all the bits and pieces of data that we gather, we can get useful information. So context is what it's all about. It allows us to build the relations over time and the relations to each other. What is the context level? That is the artificial intelligence machine learning. To cross the bridge between data and information, we need context. And this is the main development work that we do in Made in 4. It is an attempt to link the data into information by giving it the right context. If we do that, we can cross the chasm. Now I'll discuss very shortly about the role of Tower Semiconductors in Made in 4 and provide a linkage to Industry 4.0. Tower is involved in this consortium in two aspects: as a semiconductor manufacturer of VLSI devices, and second, as a supplier of CMOS imagers. Sorry. This slide is for those who want to know more about the semiconductor industry. The semiconductor industry is one of the most complicated industries in the universe. It is hell's kitchen. It takes 2 to 4 months of production time from silicon start to get a working electrical device chip. You can see on the right side a short list of operations in the manufacturing process. It relies heavily on very precise tooling, mechanical, chemical tools, electrical, physical tools. Silicon wafers used as the foundation for computer chips are made from silica, a type of sand which must be filtered and refined to 99.999% purity. This electronic grade silicon is melted and compressed into ingots, which are sliced into extremely thin, something like 0.67 millimeter thick, which we call wafers. The wafers get polished to remove any marks from the cutting. They are coated with a thin layer of photoresistant material and etched with a design of the circuitry that will be supporting using the process similar to photography. We call that photolithography. The more complicated the circuitry, the more images imprinted onto the wafer, layer upon layer, with each layer treated separately, blasted with ionized plasma, for instance, a process known as doping, or baited with metals. The finished wafer is then coated with a thin protective film before being tested, what we call the probe, to ensure that it works as intended. The main takeaway from this slide is that we must rely on reliable tools that keep doing the same thing in an accuracy out of this world. Okay, this is what I want you to understand from this slide. Precise tooling is the pillar of this industry. Now, I must emphasize previous statement. It takes 2 to 4 months to know for sure that the product is electrical function and meet the spec. Okay, 2 to 4 months. So imagine in the case that one of the tools is out of tune, we will start to get one lot after another that behaves badly in terms of electrical performance. Okay, we're testing, there are lots coming out of the line, we test them and they are bad. Now, if the bad process occurs towards the end of production, we have no problem. We can fix the machine and maybe we have 10, 20, 100, 1,000 lots in the line, in the buffer. But if the faulty tool is at the beginning of production line, okay, beginning of the production line, it means that now we have the whole production line, which is 2 to 4 months, if you recall. We have thousands, if not tens of thousands of bad wafers in the line. Can be a catastrophe. So let's consider a small example using this monitor of aluminum deposited tool. This is a real monitor of metal deposition rate. We can clearly see a drop from baseline. Okay, you can see here 2 points that below control limit. This trend is a trend over time. We see some improvement and even 1 point of data that comes back to baseline, but then it drops again. Now imagine that we will have a smart algorithm that will immediately alert the maintenance people that the tool needs to be serviced right after those first couple of points that jitter. Machine learning could easily alert in the appropriate time, indicating that the tool must be attended. Moreover, we would like machine learning to adapt this scenario and perhaps even alert before we lose control. Okay, machine learning can help us even to avoid those points at the beginning that goes below control. So you can see how critical it is to catch problems as early as possible. Now let's talk about some of the sensors that are at the peak of the industry. And by the way, sensors from silicon is in some way a gift from God and nature. We are so lucky that the silicon crystal is sensitive to photons. The energy from photons impinging the silicon crystal easily separates electrons from holes. This phenomena allows us to create the digital camera. Now, machine vision is the most mature solution used now in the industry. So far, it's being used to detect fast-moving objects, faulty products, barcode, etc. It can almost replace any manual vision in production. We can now harness this ability to recognize smaller objects much faster. Now, to demonstrate the conversion from data to information, we've selected a special use case from the automotive industry. The problem in this use case that we've selected is to detect a faulty welding spot on the driver's door of Alfa Romeo prior to final assembly. We want to catch those defects in the doors, and if we catch this defect, we scrap the door. It will not move into assembly. In this use case, Tower participates as an imager provider. We use a high-resolution, small pixel, high transfer rate to grab an image of the welding point on the driver's door, crop the image and transmit it over to the cloud. In this bench, we can grab images of final product and analyze specific elements to decide whether the product is good or not. Data is acquired by imager and travel to the cloud for analysis and decision making whether the door is good to the driver or not. Now it's not to the driver, this one is for quality. Okay, this is a quality control. Okay. In this final chapter of my presentation, I'll talk about some of the advanced sensors in the market. In the world of digital twin, which attempts to represent the shop floor in real-time cyberspace system, sensors are the key elements in this ability to provide virtual representation of the physical element in this concept. What kind of sensors? Primarily image sensors in the visible light, shortwave infrared, UV, anything. The main challenge is to transfer the data as quick as possible, map the scenery and transfer back only useful information. Now, today's high buzz for 3D mapping are the VR and AR goggles. VR stands for virtual reality, AR stands for augmented reality. Advanced OLED technology and 3D mapping technology paved the way for both VR and AR in the digital twin. Reducing the pixel size makes it possible to move the OLED display chip closer to the eye and thus reduce the VR goggle size. It allows us to make it closer to the eye. Now, time-of-flight sensors are used not just for 3D mapping of the surrounding space, but also to monitor the eye movement. So now, as you saw, I throw in another term, structure light and TOF, which means time of flight. We will discuss that in the next slide. The two most common techniques in the 3D imaging to build the virtual 3 dimension of the physical world are the time of flight and structured sensors. What is structure light? It projects stripes onto the object and read back the warpness of the reflected light. You can see how it looks on the right bottom image. This is also known as indirect measurement. The second item is time of flight, as you can see on the left image, on the bottom left. It sends out the pulses of light and measures the time it bounces back. Every nanosecond of light is 15 centimeter distance. You can assume light travels 30 centimeter in nanosecond, but we need to count the time it goes back and return. That it goes into the object and return. So we have 15 centimeters for two ways. Now, example for artificial intelligence ready in a chip is shown in one of the largest sensors of the industrial vision, which Tower Semiconductor manufactures for Teledyne. It comprises of the smallest pixel in the industrial vision sensors. It allows to increase the resolution within the same optic aperture. It contains auto detection built in within the sensor chip. But the main feature is the flexibility to speed up communication without losing information, and thus reduce the quality. So artificial intelligence and machine learning in this case are embedded in the core level of the VLSI. Now, introducing a sensor to the automotive industry is like finding the Holy Grail. There's a large span of solutions for the automotive industry, but there's no one solution that gives a whole solution. There's no one imager that actually covers everything. Only a combination of these sensors can give a holistic solution. In this slide, you can see an illustration of the output map of a LiDAR using a mirror scan. One step back from the autonomous driving system is the ADAS, Advanced Driver Assistance System. Situational awareness in automotive is mostly with image sensors. Among the sensors already in use are high dynamic range sensor, ITOF, DTOF, SPAD, SWIR imagers, etc. It's something I already mentioned in one of my earlier slides. You can see how the LiDAR here maps the image, but it doesn't give an exact 3D mapping, but a very illustration of the object. Now, another interesting algorithm that is very useful for information transfer over the cloud is the usage of gated image. Sliced image in gated pixel gives the ability to acquire only a slice of the time in space it takes for the information to get back into the sensor. For example, as shown here, you can get information only from the scene that is 15 meters from us, while ignoring all other data exist in between. On the top image, you can see the image from a standard visual camera. On the on the other images on the bottom, you can see that the camera can slice and take only the data that is close to us and ignore all the information that is beyond that space. Now, another term in the industrial vision we use, what we need for industrial vision, in fact, we need speed and accuracy. Industrial imaging spans from a low-resolution barcode readers up to LTV screens quality images with a very high resolution of 80 to 100 megapixels. For example, why do we need a global shutter in traffic control? The answer is that we can easily read the license plate of a fast-moving car. And we need this global shutter enhanced within the VLSI devices. Any mechanical shutter would fail after 10K operations. So we embed this global shutter inside the chip. A good demonstration of the global shutter in action can be seen in this slide on the upper right corner. You can see an image of rotating. Just an example from one of the exhibitions. You see a rotation of barcodes with an imager that takes an image of this rotating wheel. On the right side, you can see how it not just detecting the barcode, but you can see it also gives you the numbers that are written there. This is an example of global shutter. Now, this is a summary slide for the CIS market and its trends. The visual sensor market keeps growing every year in all of the sub-markets. You can see here the high-end photography goes up, industrial machine vision, medical, automotive, 3D, the gesture control, AR, VR, and also security. But the automotive industry with artificial intelligence and machine learning is now at the pinnacle of the development work that is being done. Tower Semiconductor covers all this market for over 25 years with well-based technology and foundry services. Now, this summarizes my presentation for today. I would like to thank you very much for listening. Thank you very much and enjoy the rest of the sessions.